Alright, today we're going to be learning about section 1-4, vacation expenses. Alright, to start off we have a warm-up, and it says to find the y-intercept of the following linear equations. Alright, so first of all, it says they're linear equations. That means when these equations are graphed, that they produce lines, obviously. But it also, there's some other things that we need to know. First of all, linear equations can be written in this form. Y equals mx plus b. Alright, so you probably remember that from your algebra days, where the m is your slope, right? Also known as your rise over your run. And the b is your y-intercept. That's where the line will cross the y-axis eventually. Alright, now the problem tells us that these are linear equations, but quite honestly we should know this going in. So we should know just by looking at what we see here, that these are linear equations, and we should know that because the equation has an x and a y. Alright, so it has an x to the first and it has a y to the first. Anytime that happens, the degree of the equation, the degree is the biggest exponent, is 1, it produces a line. So if you have y to the first but not any degree higher than that, like say a y to the second or y to the third, or an x to the first but not anything higher, like x to the second, x to the third, the y is to the first power, the x is to the first power. Therefore, we consider this a first degree equation, because 1 is the biggest exponent. And anytime that's the case, you have a linear equation. It's going to be a line. Okay, now that line might be horizontal, vertical, or diagonal, but we know it will be a straight line. Alright, now if the equation only had a y and not an x, say something like this one up here, y equals 5, that would be a horizontal line. It would go left to right, okay, or right to left. If the equation only had an x, but not a y, like that one, it would be a vertical line. It would be going up and down. When the equation has an x and a y, like all three of these problems do, all three of these warm-up problems, they all have an x and a y. That's a clue that these are diagonal lines. Alright, so these are going to be diagonal lines, and all diagonal lines are going to cross the y-axis somewhere. We just need to know where. Alright, and if we go back to our slope-intercept form right over here, that b is the y-intercept. So this is really the thing we're looking for right there, that y-intercept. Alright, so let's go ahead and get to it here. We want to put these equations into slope-intercept form if they're not already done for us. Alright, so the first equation is already in slope-intercept form. We have y equals mx plus b. Alright, now it has minus 11, but that's just like adding negative 11, right? So this, y equals mx plus b, the b is negative 11. Alright, so the y-intercept is at negative 11. Alright, so imagine, a graph where this is your x-axis, this is your y-axis. Right, and got funky on this all of a sudden. This is the y-axis. Alright, if the y-intercept is at negative 11, that's going to be down here somewhere, right? The slope is positive, so it's going to be an upward facing line. So it's going to look something like that, right? Kind of an ugly line, but you understand the point. Alright, so that's what's going on here. Now, the y-intercept is this point right there. It's where the point crosses, where the line crosses the y-axis, and that actually is a coordinate. So our b is negative 11, but it doesn't ask in the problem what is b. It asks to find the y-intercept. Right, the y-intercept is right here, and that is a coordinate, and the coordinate is at 0, negative 11. Right? So the b is negative 11, but the y-intercept is at 0, negative 11. Alright, so always remember to know that that's a coordinate. Alright, now the next equation. There's an x and a y, right? There's your x, there's your y, but it's not quite in slope-intercept form. Instead of y equals mx plus b, it looks like it's in y equals b plus mx form. In other words, the mx term and the b are in the wrong position. All right, so let's just go ahead and trade those out. Trade that, and if we were to do that, we would get y equals 3x plus 7. All right, and now the b would be 7, meaning the y-intercept would be at 0. Let's do some weird stuff there. Let's try that again. The y-intercept would be at 0, comma, positive 7. All right, so there's your y-intercept for number 2. All right, and the last problem. The last problem, it is not in slope-intercept form. So notice slope-intercept form, like we have, over here, the y is isolated on the left side. The y is all by itself. That's not what we have in number 3. The y term is actually on the right side, and the x term, which should be on the right side, is on the left side. So what we want to do is swap these things. Now you got to be careful. You can't just change sides of an equation willy-nilly. Now the one above, number 2, right, the 7 and the 3x, we could swap positions because they were on the same side of the equation. Right? If they're on the same side, that's no problem to just move them around on the same side of the equation. But when your x and y are on opposite sides, right, like here, okay, we want to move those. When you want to move a term over to the other side of the equation, in other words, it's going to need to cross over that equal sign, you can't just move it, right? You've got to actually do an operation that will cause it to move. So if I want that 6y to be on the left side, I'm going to go ahead and subtract it. So I'm going to subtract 6y over to the other side. Now the 6y's will cancel. Coming over here for a little extra room, that's going to give me either 3x minus 6y, or I can think of this as negative 6y plus 3x equals negative 12. All right. And remember, we are trying to get the y by itself here. All right, so I'm going to erase this stuff, get it out of the way for us. A little more room. So I'm trying to get that y by itself. So look at what's going on there. To get the y by itself, a couple things need to happen. The negative 6 that's in front of the y has to go away, and the plus 3x has to go away. All right, so let's move that 3x over. If it's in slope-intercept form like this, the x term should be on the right, not the left. All right, so I'm going to move this 3x term over. I'm going to do that by doing the inverse operation. Right, the inverse of adding 3x is subtracting 3x. And whatever I do to one side, I must do to the other side. That keeps my equation balanced. And I get negative 6y equals negative 3x minus 12. All right, coming over here for a little more room. I have negative 6y equals negative 3x minus 12. All right. And now I'm going to get that y by itself. All right, so I need to get rid of the negative 6. So you got to think about, well, what is the negative 6 doing to the y? What mathematical operation is happening here? So negative 6y means negative 6 times y. All right, so I need to get rid of multiplying by negative 6. And the way I get rid of multiplication is the inverse operation. I'm going to divide by negative 6. So I divide the left side by negative 6. I must also then divide the right side by negative 6. And I get an equation that says y equals, now I have a negative 3x over a negative 6. Well, negative 3 over negative 6. Negative over negative turns positive, right? And 3 over 6 reduces down to 1/2. So that becomes positive 1/2. So that's 1/2 x. And then I also have the negative 12 being divided by negative 6. Well, negative 12 divided by negative 6 is positive 2. All right? So that positive 2 is the b, all right? Meaning it's on the y-axis at positive 2, and that means the coordinate is 0, 2. That is your y-intercept. All right? So there are 3 different equations with 3 different y-intercepts. All of them are diagonal lines, and now we know where they cross the y-axis. All right, so when graphing lines, always a good idea to know where your intercepts are. All right, in this case, the y-intercepts. All right, so some vocabulary for this section. So this section we really get heavy into talking about normal distribution, bell curves. If you've ever heard of grading on the curve, we're actually going to be learning about some of that stuff today. All right. So the first term we need to talk about is raw data. Raw data is comprised of raw scores. All right. So what that means is, think about like raw food. Raw food means it's unprepared, right? So raw data is unprepared data. It's data that is not prepared for any kind of statistical analysis. All right. In other words, there's no frame of reference. It's just a bunch of numbers that don't really give you any meaning, right? So it's not something really prepared and ready to use yet. So raw data is not ideal because we can't really get any information or meaning out of it. All right. So a lot of times what we do is, if we have raw data that doesn't have any frame of reference, any kind of meaning behind it, we will oftentimes in statistics convert that raw data into standard scores or standardized scores. All right. And a lot of times that's using something called a z-score. All right. So we'll be getting into that soon. But basically, when you standardize a score, when you create a z-score, what you're doing is you're giving it a frame of reference. So you have all this data, right, all these numbers all over the place. What it really does is kind of compare all the data values to the mean. You know, is it above the mean? Is it below the mean? Is it, you know, a little above or a lot above? Or is it a little below the mean or a lot below the mean? All right, z-scores are used to standardize your scores, so that, you know, if I just tell you, hey, I got a, 82 on a test, well, you might go, oh, good, that's 82%. Well, what if I got 82 correct out of 82, right? Now I have a frame of reference. It's 82 out of 82 is 100%, not 82%, right? Or what if I got a 95 on the test? You say, oh, great job, right? Well, what if I say, yeah, I got 95 questions right, but there were, 10,000 questions on the test, right? Well, now you only got 95 right. It doesn't sound so good, right? So that's kind of like a frame of reference, right? And statistically, what we often want to do for the frame of reference is to compare it to the mean. All right. Now, all of you have actually taken tests like the CASP test. Most of you have probably taken the SAT or the PSAT or maybe the ACT. Right? So you've taken, maybe some of you have taken an IQ test before. All of those are what are considered standardized tests. So you've probably heard that term before, standardized testing, standardized tests. Standardized tests are tests where instead of giving you a percentage, like an 87%, oh, that's a B, or like, maybe a 79% as a C+, right? So instead of giving you scores like that, these standardized scores instead compare you to the average, to the mean. They compare how you did to the average, the mean. All right. Now, the reason they do that is because a lot of times, you think about something like a test, right? They can't keep the test the same every year, so they got to change it. They're changing the SAT multiple times a year. They're changing, AP tests multiple times a year. They can't have the same IQ test, or somebody would study for it and look like a genius when they're not, right? So they're constantly changing the test, so they can't really, if I might one year get 85 correct on the test, and then they change it the next year, and maybe the next year I get an 82, right? And maybe it's just due to changing the test. So instead of giving you like a percentage or a letter value, what they do is they compare you to the mean. They see how did everybody do on that test. They find the mean, and then they compare how you did to the mean. Did you score above it or below it? Did you score way above it or way below it? A little above it or a little below it, right? And that's called standardizing your scores. So that's kind of the process of taking a raw score that doesn't really have any frame of reference or meaning and converting it into a form that does have a frame of reference, that does have some meaning. It gives you a z-score, and that tells you where it is relative to the mean. Alright, so an example of this is a z-score of positive 2. Alright, so anytime you see a z-score that's positive, that means the data value or the data score is higher than the mean. It's above the mean or greater than the mean. So a z-score of positive 2 means that the data value, the data score, is 2 standard deviations above the mean. A z-score of positive 3 would mean 3 standard deviations above the mean, right? A z-score of 3.5 means 3.5 standard deviations above the mean, so on and so forth. All right, now a z-score that's negative means that the data value or the data score is lower than the mean. It's below the mean. All right, so a z-score of negative 1.5 is equivalent to 1.5 standard deviations below the mean. Right, a z-score of negative 2 means the data value, the data score, is 2 standard deviations below the mean. All right, so that's what a z-score is. It standardizes the score in such a way to tell you how it compares to the mean, and the way it talks about, distance away from the mean, how far it is away from the mean, is by telling you how many standard deviations it is, either above or below the mean. All right, so let's talk about normal distribution. All right, normal distribution is a really, really important thing in statistics. It's really a very important thing in life in general, to be quite honest with you. Basically, normal distribution is kind of a natural occurring thing, a natural occurring phenomenon where data behaves in a very predictable way, right? And basically the way this works is the more and more data you collect, the more and more likely that data is to be normally distributed. All right, and we'll talk about what that means, normally distributed, here in just a second. But essentially what we need to know, at least for this slide, is that normal distribution is actually kind of the natural way of things, right? It's the natural state of being for data, and the more and more data you collect, the more and more likely it will be to follow a normally distributed pattern. Okay. All right. Now, because it's so prevalent, data behaving in a normally distributed way, because that's so prevalent, we can use it to make a lot of predictions, right? It's very predictable. All right, so normal distribution is really a way of predicting future values, or at least that's one of the uses for normal distribution. All right, so I talked a minute ago about normal distribution, how data tends to be normally distributed the more and more of it you collect. All right, so what exactly does that mean? All right, so here's some things you need to know about normal distribution. All right, our measures of central tendency, the mean, the median, and the mode, are equal. All right, so in normally distributed data, the mean, the average, the median, the middle term, the middle value, and the mode, the most frequent value, are all the same. All right, if they are not, then it is not normally distributed data. But I just told you, normally distributed data is very common. It's very prevalent, right? So the more and more data you collect, the more and more likely it becomes that the mean, the median, and the mode are equal. All right. In other words, think about it this way: if I, take somebody, kind of ask everybody's height, right? The more and more people I ask, the more closer and closer I'm going to get to the true average, right, height in, say, America, right? If I only ask people, say, in your house right now, maybe your family members tend to be taller than average, or maybe shorter than average, right? If I only ask people in your household, how tall are you, I might not get data that kind of is normally distributed, right? If I ask people at Great Oak High School, and I ask everybody there, right, I'll probably get a little bit closer to normally distributed data, but even then I'm only asking teenagers at that point, right? So to get a true idea for what those heights really are, the mean, the median, mode, I would want to get as much data as possible. All right, and the more and more I get, the more and more likely it is that the mean, median, mode are all the same. All right, also, another thing about normal distribution is that the data values, the scores, tend to be clustered around the mean. Now, what do I mean by that? I mean that, say you have an average height, say an average height of a man in the United States is 5'10". Okay, if I go and ask a bunch of men, how tall are they, assuming that I'm getting truthful answers from them, when I get answers back, I'm going to get a lot of answers of men who are, 5'8", 5'9", 5'10", 5'11", maybe 6 foot. I'm going to have a lot of people right around in that range. Think about most of the men probably somewhere between 5'8" and 6 foot, most of them, right? Maybe some are right on the average, 5'10". Maybe some are a little bit shorter, a little bit taller, right? But most men you will come across are somewhere in that range. They're close to the mean. Their heights are clustered close to the mean, right? The further and further you get away from the mean, say like instead of 5'10", you pass beyond 6 foot and go to 6, you go to 6'9", you go to 7 foot, right? The taller and taller people get, the less and less often you see people of those heights, right? So you have a lot of your data values, which are men's heights, would be very closely clustered toward the average, toward the mean. And then the further you get away from that average, either way taller than the average, the mean, or way shorter than the mean, you're going to see fewer and fewer of those in the population, right? There's less and less frequency, all right? All right, now the data is denser toward the center and less dense toward the tail. So this kind of says the same thing as the characteristic above, only above I used it in terms of describing how much of the data you'd see. When I say the data is denser toward the center and less dense toward the tails, I mean what it looks like when it's graphed. All right, so when it's graphed, you're going to see a lot, like the graph is very tall toward the center. There's a lot of data in there, and then it kind of tapers off toward the tails. All right, so it gets kind of shorter and shorter and shorter until eventually it gets, negligible, near zero. All right, next one. The graph of normally distributed data is bell-shaped. All right, so you probably have heard of the bell curve before. If not, I'm sure you've heard of, teachers grading on the curve, right? These are all talking about the same thing. It's talking about normally distributed data. It is curved in such a way that when it's graphed, it's the shape of a bell. All right, and you'll see that bell shape here in just a minute. All right, and the next one is the graph is asymptotic to the horizontal axis. All right, so think about a graph, right? When things are graphed, you have a vertical axis and a horizontal axis. All right, so here's your vertical axis, here's your horizontal axis. Usually the vertical axis is considered the y-axis, the horizontal axis is considered the x-axis, right? What it means when it's bell-shaped is that it's going to go up and then come back down again like a bell. All right, so notice that looks like, Taco Bell symbol or something, right? Now, the bell doesn't ever actually touch this x-axis, this horizontal axis. It just gets closer and closer and closer to it, but never quite touching it. So you probably remember from your days in Algebra 2, you learned about asymptotes. So an asymptote is a line that a curve approaches. It gets closer and closer and closer, in fact, infinitely closer, but it never actually gets to it. Imagine I told you to stand up, walk halfway to the wall across the room, and then take another step, walk halfway to the wall again, and then take another step, walk halfway to the wall. If you're always only going half the distance there, you're never going to actually reach it. You're just going to go shorter and shorter steps, but you'll never actually get it because you're always only going half the way. All right, so it's kind of the same thing here. This bell, right? right, is getting closer and closer to this x-axis down here, but it's never actually going to touch. It's going to curve and just get close, 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 infinitely close, but won't touch. All right, we call that x-axis an asymptote. So the curve follows asymptotic behavior, right? It behaves in such a way that is as though the x-axis is an asymptote, where it will get closer and closer and closer, just won't touch it. All right, so I am an ugly artist, so here's a much better picture of what the normal or bell curve looks like. Okay. Now, with a bell curve, with normal curve, normally distributed data, right? Notice it is bell-shaped, and notice how the purple curve doesn't ever actually touch the line below, the horizontal line. It's getting close to it, but it won't touch it. All right? In my drawing, it kind of looked like it did, so this is a much better drawing than what I had. All right, now notice that if I were to, maybe extend this a little bit, let's get this extended. So take this horizontal axis and extend it, and then come up here. If I call this the frequency, notice right here in the middle of the graph, I have the highest frequency right there. Okay. Now you hopefully remember from section 1.1, what do we call the data value that has the highest frequency? We call that the mode, right? So if it has the highest frequency, that has to be the mode. So that means right here in the middle of the bell curve is where our mode is. Okay? Now, notice that the purple curve there, that bell curve, appears to be kind of a mirror image of itself. In other words, the right side and left side look exactly the same, and they are. All right, bell curves are symmetric. So symmetrical means that they are the exact same on the right side as they are on the left side. It is a mirror image. So this line right here that I just drew, that we know, hey, the mode is right there. Well, that also denotes another important thing, and that is that half the graph is on the right and the other half is on the left. So think about where, what do we call the term that's right in the middle, where half of the values are bigger, half the values are smaller. Half the values are to the right, half the values are to the left. It's right there, smack dab in the middle, so that's also considered the median. All right, so right there, right along that line, we have the median and the mode. All right, and now because we have it being symmetric, right, I have just as much on the right as I have on the left. The curve, because it's the same on the right and on the left, that means all the values on the right are the same distance above the mean, that all the values on the left are below the mean. So the amount that's above the mean and the amount that's below the median, the middle, the amount that's above the middle, the amount that's below the middle, kind of cancel each other out, meaning this is not just the median, but it's also the mean. All right. So right here, I have the mean, the median, and the mode. All right. So normal distribution must have that. The mean, median, and mode are all located in the same spot. They're all the same value. All right. So that's something important to know. All right. So we do have some normally distributed data. Now let's look a little bit closer at this stuff. Okay. So I'm going to get rid of stuff that I just put in there. All right. So normally distributed data, I told you before, is very predictable. In fact, it's so predictable that there's something called the empirical rule. And that's down there at the bottom of your screen right now. The empirical rule is also sometimes known as the 68, 95, 99.7 rule. Okay? And what this is telling you is that 68, roughly, approximately, 68% of your data lies within one standard deviation of the mean. All right, so what we have here is we have our mean right here. It's there is our mean. Okay? Alright, so if that's our mean, what we have is over here, between 0 and positive 1, remember our z-scores, these are our z-scores down there, these are our standard deviations. Between 0 standard deviations away from the mean, that means you're on the mean, and 1 standard deviation above the mean, between those two, see how there's about 38 or about 34% of your data? So you have about 34% of your data that's within 1 standard deviation above the mean, and then you have another 34% roughly of your data that's within 1 standard deviation below the mean. So that means we have a total of 34 and 34. We have a total of 68% of our data is found within 1 standard deviation plus or minus of the mean. Alright, now the next kind of section out. So let me put this in a different color and make this maybe a little bit easier to see. So now let's go from 0, which means 0 standard deviations away from the mean. That means you are on the mean right here, right? Okay. So from the mean out to here, now we're talking about 2 standard deviations above the mean. So from the mean, right there, to this blue line out here, that's within 2 standard deviations of the mean, right? Or if I go this way to here, I've gone 2 standard deviations below the mean. See that -2, okay? All right. So essentially what I added was this, which is approximately 13.5%, and this, which is also approximately 13.5%. Right? So what I really added was another 13.5% and another 13.5%. In other words, I added 27%. Well, if I take my 68% that I already had in red, and I add this 27% that I just got by going out 1 more standard deviation, I get a total of 95%. So I have 95% total of my data lies within 2 standard deviations of the mean. Alright, so let's go a little bit further here. And there's some rounding going on, so this isn't totally exact. But here, if I go from the mean, right there in the middle, out to 3 standard deviations, now I'm adding another roughly, 2 and some change percent on that side. If I go from the mean out this way to a 3rd standard deviation, I get another little bit over 2%. So together, all these percentages make up about 99.7%. So I've added, approximately 4.7%-ish. It's not quite exactly that way because I had rounding before, but you get the point. It goes up to about 99.7%. Right? So what we need to see here is that very little of the data, in fact, just this much, that looks like 13%, it's actually 0.13%, I cut off some of that, and this part, 0.13%. So only this 0.13% and this 0.13%, so 0.13% plus 0.13%, okay, is 0.26%, which is approximately 0.3%. Only about 0.3% of the data will go beyond 3 standard deviations. So more than 3 standard deviations above the mean, like to the right, or more than 3 standard deviations less than the mean, so to the left of the mean. So in other words, almost all of your data, so if 99.7% is within 3 standard deviations, that means 0.3% lies beyond 3 standard deviations, right, of the mean. All right, so remember what I said earlier. This is very, very predictable. All right, so how your data compares to the mean in terms of its standard deviations is very, very predictable. So knowing that this will pretty much always be the case, that your data, at least if you have a lot of it, is going to follow this predictable pattern, you can get 99.7% of your data being within 3 standard deviations. So think about this. If you, say, ran a company and you were trying to maximize your sales, right, like maximize your customers, you know that 99.7% are going to be within 3 standard deviations of your mean. Just find your mean, find your standard deviation, and go out 3 standard deviations above, go below 3 standard deviations, and 99.7% of your customers are going to come within that range. So maybe it's shoe sizes, right? Or maybe it's dress sizes, or maybe it's, hat sizes, right? If you're talking clothes. But there's all kinds of, examples of how this can be used. All right, so that's what the normal curve looks like. So let's look at an example. IQ tests, I mentioned earlier, are normalized tests. These are standardized test scores. All right, so they are normed around the mean. All right, so in an IQ test, the mean is 100 and the standard deviation is 15. All right, so we've got our mean right there in the middle. All right, so that's, remember, the mean, the median, and the mode. Okay, now this is a good time to point something out. When we have talked about the mean before, we have used x bar. Right? X bar is the sample mean. So that means it's the mean or average of a small sample, a portion of the population, a subset. All right. This, remember, normal distribution. You get normally distributed data by collecting a lot of it. So it's not really a sample. What you're really looking at is the population. So we have a symbol, and it's called mu. It kind of looks like maybe a cursive letter M. Looks like a cross between an M and a U. So it's mu is the name of it. It's a Greek letter like pi or sigma, right? Mu means the population mean. All right, so when we're dealing with normal distribution, we're not looking at x bar, the sample mean. We're looking at mu. All right, so this right here, this 100 is mu. That is the population mean. So that means that's the mean of the entire population. So if I were to go around and ask, 100, 1,000, 100,000, a million Americans, and I ran an IQ test on them, that I would get a mean of 100. Right? So the test is actually set up and graded so that whatever the average is, they just call that 100 for an IQ. All right. And then a standard deviation is 15. So notice, to go from here to here, I go up by 15, right? I go to 115. Go up another 15, I go to here, another 15, I go to here, right? So in other words, this right here, let me do this in red to make it stand out, this right here has a z-score of positive 1. This right here has a z-score of positive 2. This right here has a z-score of positive 3. Because all of those are, look at the numbers. 100, 115, 130, 145. They're getting bigger and bigger. They're higher than the mean. All right, now over here, I'm 1 standard deviation, 15, below the mean. So 100 minus 15 is 85. So now my z-score is -1. If I subtract another standard deviation, another 15, it goes down to 70. So this has a z-score of -2. If I subtract another 15, another standard deviation, I get here to 55, which is a z-score of -3. All right. So remember what our empirical rule tells us, right? The empirical rule is also known as the 68, 95, 99.7 rule, right? So we have the 68, 95, 99.7 rule, and that is the empirical rule, okay? All right, so let's look at this. Part A, this example says, what percentage of people have an IQ between 85 and 115? Okay, so between 85 and 115. All right, so 68% of your data is going to be within one standard deviation. All right, so it might be up to one standard deviation above the mean, this way, or it might be down to one standard deviation below the mean, that way, but 68% of your data will be between those two markers, between here and here. Okay, the one on the right is one standard deviation above the mean. This one on the left is one standard deviation below the mean. So 68% of your data is going to be within that range. All right, let's look at part B. What percent of people have an IQ above 100? Now, you might be tempted to actually put in those percentages, but there's a much easier way. Remember, this is the median. That 100 that's going right down the middle, right? This one right here, this score, this IQ score, 100, that is the population mean mu. But remember, normally distributed, the mean, the median, and the mode are all the same. Okay, so that's the median, meaning half the values are to the right and half the values are to the left. So when it says what percentage of people have an IQ above 100, that would be all of these people, from this line all the way over. Okay, well, 50% of the data is to the right, 50% of the data is to the left. Okay, because it's the median, right? The median's right in the middle. So 50% of your data will have an IQ above 100. All right, now let's look to part C. What percent of people have an IQ below 85%? All right, now this one's a little bit trickier. All right, so what I'm going to do is I'm going to go through and erase something that I already put in there because I don't want it to confuse us. So this thing right in the middle, 64 or 68. Remember, the way we got that was by saying, okay, well, yeah, that 68% right there, where did that come from? All right, well, it came from the right color. All right, so it came from 34% of the data being in that section, and the other 34% of the data being in that section. Okay? Now our question is, what percent of people have an IQ below 85? Now to me, the easiest way here is this. Look at your answer above in part B. It says, what percent of people have an IQ above 100? So we know that all the people on the right side of the mean, in other words, all these people over here, all of this that's in green is all 50%. Right? It's half the data. Well, from the middle, that black line down the middle, to the right is 50%. This section right in here right here, this section is 34%. So if I take my 50% that's on the right, and now I add the 34% that comes from this section right here, together I get a total of 84%. So that means 84% comes from this line over, that way. Alright, so I've got 84% of my data to the right. Well, if 84% is to the right, then that means 16% must be to the left. Okay? So I have 16% to the left because the other 84% is to the right. 16 plus 84 is 100%. That's all our data. All right, so that's probably the easiest way to go about doing it. Now, you could, if you wanted to, go back to the slide before and remember this right here, when it said this, the percentage of people have an IQ below 85, that's all of these people to the left of this z-score, -1. All right? Well, look, here's a z-score of -1. So I could add this one, and this one together. And if I add this, and this, I get about 16%. All right? So that would be another way to do it. Alright, so now let's consider this question here. It says, how might you find the percentage of people with an IQ higher than 125? So let's go back to the previous slide. What I just asked you was people who had an IQ between 85 and 115. There are those numbers. I gave another question was people have an IQ above 100. I gave you that IQ. What percent of people have an IQ below 85? That's this one right here again, right? So all the values that I just had you use in example 1, I was giving you IQs that were exact standard deviations away from the mean. So like 100 is exactly the mean. It's 0 standard deviations away from the mean. 115 is 1 standard deviation above the mean. 85 is 1 standard deviation below the mean. Right? So we were looking at data values that were either on the mean or exactly 1 standard deviation above or exactly 1 standard deviation below the mean. So let's look at this question here. Okay, it says how much you find the percentage of people with an IQ higher than 125. So where would 125 be on this thing? To me, 125 looks like it would be right about there. Okay. So it's asking, what's the percentage of all these people in here? Okay. Well, if it was, let's go through and label our z-scores again. So remember, this is the mean, and at the mean, the z-score is 0. Here my z-score is +1. Right here, my z-score is +2. Right here, my z-score is +3. Right? Down here, my z-score is -1. Here, my z-score is -2. Here, my z-score is -3. Okay. Now, what we did in the last example was we were using these kind of numbers that give you z-scores that are whole numbers, like 1, 2, 3, right? The z-scores were integers, right? Well, in this example right here, when it's asking for people with an IQ higher than 125, look where 125 is. It's in between a z-score of +1 and +2. So this 125 has a z-score of 1 point something, right? It's something between 1 and 2, but we don't know exactly. All right? So how can we know exactly what that z-score is? Okay? Here's how to do it. Okay? You get yourself a z-score using this formula right here. So this formula says your z-score z is going to equal your x, which is your raw score, or your data value, minus mu. Remember mu we just talked about. Let's see how that looks like a cross between an m and a u. It's mu. A little bit m, a little bit u makes a mu. Alright, so x minus mu. X is your data value, your raw score. Now you subtract the mean, the population mean mu, and then you divide by this guy right here. So that guy right there is lowercase sigma. So Greek letters have uppercase and lowercase. That's lowercase sigma. And lowercase sigma is used to denote the population standard deviation. All right, so we spent our last section, section 1.3, talking about how to calculate the population standard deviation, and that's what you use. That's why we did it last section, so we could use it in this section. And we use that population standard deviation. All right, now that's a pretty important formula for you to know, because a lot of what we do in this chapter does kind of revolve around standard deviation in one way or another. And usually when you are talking about standard deviation, there are some z-scores involved that you're going to need to create. All right, and I did say you need to create your z-scores. You are going to make the z-scores usually. You are going to create them. All right. Now, the wonderful thing about z-scores is that, like all normally distributed data, it is predictable. All right. You've got, I actually have two tables of z-scores. So I've got this table on the left, and I've got this table on the right. Okay. Now the table on the left has, see where this line is right there. See how it's on the left side of the mean? It's on the left side of the peak of that bell curve. That means it's to the left of the mean. That means it's less than the mean. Well, we talked about it earlier. When a number is less than the mean, it's going to have a negative z-score. So the table that you see on the left is for anything with a negative z-score. Negative anything. Okay? Now look at this line right here. Whoops. Doing a good job of controlling my pen here. Alright, so let's look at this line right here. Okay, that's to the right of the peak. That's to the right of the top of the bell curve. Alright, and so that means since it's to the right, it's that whatever number, it's bigger than the mean. Right? Any number bigger than the mean will have a positive z-score. All right? So look at your z-score columns right here. Okay? All the way down here. All of those z-scores are negative. Okay? Now look at the z-scores here in the other table. All of these z-scores, so these ones are negative. These z-scores are positive. All right? So this is a pretty packed, sheet of values, right? It's packed with z-scores and corresponding percentages, right? And so it's so packed that it usually won't fit on one page. So there's usually a page for negative z-scores and a different page for positive z-scores. All right, now just so you know, this is a good place to stop. I have posted this same table of z-scores on my Canvas page. All right, so you have this exact file that you can look at. So you can look at it, now if you like, or after the lesson. But you will need to have access to this. All right, to z-scores. So there's a couple places you can find this. First of all, I just told you they're on Canvas. Right? So I have this file on Canvas so you can have your own z-scores on your computer with you at all times. Okay. Another place is there is in your textbook, there is a table of z-scores there in the back in the appendix. So you can always look there. I know I'm asking you to actually crack open that textbook, dust it off, and look inside of it. And you will find in the appendix near the back, there is a table of z-scores like this. Okay. A third option is do what, quite frankly, surprises me that people don't do more often. Just Google it. Just Google table of z-scores, and you'll probably get, hundreds of thousands of websites where you can, it'll show you a table of z-scores. Right? So you can find these in lots of different places. You just got to look. All right. So the reason why we want to create z-scores and then look at a z-score table is because it tells us some important information. Okay, so let's look at this example. I'm going to actually do that here in number 2. It says, what percentage of people have an IQ above 125? Well, 125 is right about here. All right, so let's get a z-score for that 125. So the way we get a z-score is we take the x value and we subtract the mu and we divide by sigma. So our z-score is going to be our data value. That's x. So the x is that data value, 125, minus the mu. Right? And the mu is this guy right there. It's 100. And we're going to divide by sigma. And sigma is the standard deviation. Right, so where does the standard deviation come from? Standard deviation comes from here. It's the distance between 100 and 115. It's the distance between that. That distance is 15. All right, so simplifying this, I get 125 minus 100, that's 25, over 15. And reducing that fraction, I could do, but usually you see z-scores in like a decimal format. So 25 over 15, that's 1 and 10/15. That's 1 and 2/3, which is 1.6 bar. Usually with z-scores, you will see them rounded to 2 decimal places. So I rounded it to 1.67. Okay, so this 125 has a z-score equivalent of 1.67. All right, so let's talk about that. 125 is the raw score. All right, so if you just ran up to a random person and yelled at them, "I got 125," they'd probably look at you weird and say, "Well, all right, congratulations. I have no idea what you're talking about." Right? But if you ran up to somebody and said, "Hey, I got a z-score of 1.67," if that person knows anything about statistics, they're going to say, "Hey, that's pretty good. That's 1.67 standard deviations above the mean," meaning you did a lot better than the average person on whatever it was that you did. All right. So let's look at how can we find the percentage of people whose IQ is above 125. All right. We're going to use this z-score. So this z-score is 1.67. Now that's important because I can go back to the previous page and I can find that z-score on the table. So let's look at it. Okay, now I'm going to put this in another color so it stands out a little bit. Okay. Notice these z-scores. All right, and they're kind of small right now, but if you can zoom on your screen, go for it. You guys got young eyes, so you might see it better than me. But notice those z-scores have 2 decimal places. There's a number before the decimal, there's a number after the decimal place. Well, how is that going to work if I'm looking for a z-score of, remember, 1.67? So this part right here, actually, let me fix that and make it stand out. So my z-score is 1.67. Okay? So this part right here comes from there, 1.6. So I got to find it. So 1.6 is right there. I just circled it. There's 1.6. Okay. Okay. So there's 1.6. So that's that part. Well, now I need the 7 that comes after the 1.6. So notice that is, there's the 6, then the 7. So the 7 is actually 2 after the decimal place. So I'm going to find where is there a 7 that's 2 after the decimal place. So where's this, right? I have a decimal place, then a number, then a 7. All right, so let's find that now at the top here. So there's 0.00, 0.01, 02, 03, 04, 05, 06, 07 is right there. So that's where that comes from. So what I need to do is I need to find where does this row, or sorry, this column, the 0.07 column, and this row, the 1.6 row, where do those collide? Okay? And if you look at them, they collide right here. Okay. Maybe not the best job with the pen right there. Let's try that again. It's right there, 0.9525. Alright, so 0.9525. Alright, so let's write that down here. 0.9525. Alright, now that's a decimal. Now we've talked in this class about how to convert decimals to percentages. So I would multiply by 100 to get a percent, and that would be 95.25%. Okay? So 95.25%. Alright, so what does that mean? Let's look at this picture up here. In this picture, notice I have the line where my z-score is right there, and then everything else is to the left. Okay? Notice there's a lot of the curve to the left and not much of the curve to the right. So this 95.25% is right there. So it's telling you 95.25% of your data is to the left of that z-score. Well, if 95.25% is to the left, that means this little unshaded section must be the other 4.75%. All right? Because they got to add up to 100, right? Those two. Alright, so those add up to 100. I got 95.25 and 4.75. Those add up to 100%. So 95.25 is to the left of my z-score. In other words, to the left of my data value. And to the left means less than. So 95.25% are less than that data value. To the right is greater than. So that unshaded area is the 4.75% of data that is greater than my data value. Alright, so let's look at which one we're talking about. It says, how could you find percentage of people whose IQ is above 125? So that's all these people over there. So look at that. Does that look like it might be 95% of the data to the right and 5% to the left? Or does it look like 95.25% of your data is to the left, and the other 4.75% is to the right? Okay, so 4.75% of people have an IQ above 125. All right, and that means the other 95.25% have an IQ below 125. All right, so IQ, just in case you are wondering what an IQ test is, maybe you've never seen one, it's an intelligence quotient, so it's kind of testing your intelligence. All right, so that's what, how to do these. All right, we just used a z-score. Now before, we were using the empirical rule when the values fell right on a whole numbered z-score, like that was a z-score of 1, this 130 was a z-score of 2, so this one right here was in between. It was a z-score of 1.67. So that's why we had to use the table on this one. The other one, the previous example, in example 1, I didn't use a table because I could just use the empirical rule, the 68, 95, 99.7 rule. Alright, so this kind of talks through the steps that we just did. It's a little bit easier to see now, so we got our z-score right. So we had our z-score of 1.67. Okay, so here's where the 1.6 is, here's where the 0.7 is. Those collide right there, so that's where your 0.9525% comes from. So 95.25% is to the left. The z-table always tells you the percentage that's to the left. Always. Okay. and that's why you see it's shaded into the left there, right? All right, and now we got to subtract that from 1, 100%, right? So if I did 100% minus this amount that's to the left, it's going to give me the amount, this was what goes to the left, it's going to give me the amount to the right. Okay, so this slide just kind of talks you through step by step how to do what I just showed you a minute ago. All right. All right, let's look at this example. All right, so here's one that maybe hits home for you guys. It says an IQ higher than 142 is considered to be genius level. All right, so if there's probably a lot of kids walking around Great Oak, or used to walk around Great Oak, now they're at home, distance learning, but a lot of kids at Great Oak probably think of themselves as geniuses, right? But how many actually are? Let's do the math. Let's figure out how many students at Great Oak really would be considered genius level. All right? So 3,300 students at Great Oak have their IQs tested. How many of them will be considered to be geniuses? All right. So we know because it's an IQ test that this is normal distribution. So anytime you have normal distribution, it might already be done for you. It might not be. Okay? In this case, it's not. What you should always start these problems with is a bell curve. So draw yourself a bell curve. That's kind of an ugly one, right? But we get the point. As you guys, I'm sure, noticed already, I'm kind of a terrible artist. So bear with me. Draw yourself a bell curve. There we go. All right. Now on that bell curve, remember your mean, median, and mode are all right in the same place. Your mean, median, mode are right here at the peak. So right there, that should be right in the middle. That's your mu. Right? That's your mean, median, and mode. Okay? Now at that mu, at that population mean, the z-score is 0. All right, remember a z-score is how many standard deviations you are above or below the mean. So if your z-score is 0, that means you are 0 standard deviations above or below the mean, meaning you are exactly right on the mean. All right, now over here I'd have a z-score of positive 1. Shoot, get rid of that thing. So here I have a z-score of positive 1. Here I have a z-score of positive 2. And here I have a z-score of positive 3. All right, now let's do the same thing on the other side. Remember on the right side, the z-scores are positive. On the left side, they are negative. All right, so there is our bell curve. It's kind of ugly, but we get the point. So we've got our negative z-scores on the left, our positive z-scores on the right. All right, so those are the z-scores. Now, anytime you're doing any kind of normal distribution, start with what I just did. Okay, now notice, nowhere in there does it say anything about an IQ of 100 or anything like that, right? What I just did was I did it using z-scores instead of the actual data values, the raw score. All right, so anytime you have a normally distributed problem, normally distributed data, this should be the number one first thing you do. Draw yourself a bell curve and put in your z-scores. I don't even need to look at the rest of the problem. If I were reading this problem, I would get to this second word and stop. And I would do what I just did, draw a bell curve and put in my z-scores. The reason why is I know IQ tests are normally distributed, and as soon as I hear those words, normally distributed, as soon as I read those words, normally distributed, I know I must draw myself a bell curve. And with that bell curve, I should be putting in my z-scores. All right, now what you want to do next is put in the raw scores that correspond to these z-scores. So like right here, z-score of 0 means you're right on the mean, right on the mu. Well, we know from the previous problems that in IQ, and that's kind of hard to see, I'm going to use a different color here. When it comes to IQ, 100 is the mean. Okay, so let's put in a better color for this. Let's put in yellow, maybe yellow where it shows up better. There we go, 100. Okay, so that's our that's our raw score. The z-score is 0, but the actual IQ score is 100. That's the raw score. All right. Now, because we know the population mean is 100, and the standard deviation is 15 for IQ tests, and once again we know this because it told us it in example 1 and 2. All right. A z-score of 1 would have one of these standard deviations added to it, so it would be 115. A z-score of 2 would have 2 of these added, so now it'd be 2 of those would make 30, so it'd be 130. A z-score of positive 3 means add 3 standard deviations, so add 3 of these, that's 45, so I get 145. Okay. And on the left side, I go the opposite way because they're negative. Now I'm subtracting these standard deviations. So I subtract a standard deviation of 15, and it gives me 85. Subtract another 15 standard deviation, I get down to 70. Subtract another standard deviation of 15, I get down to 55. All right. So the red scores are my standard scores, my z-scores. The yellow scores are the actual data values, the actual raw score that people get on the IQ test. All right, so now it says an IQ higher than 142 is considered to be genius. All right, so what we're looking for, let's look for where is 142 on this right here, right? So where is that thing? All right, so I look here and I appear to see 142 being pretty much like right there. Right, so there's 142. All right, so in order to be a genius, they have to have an IQ higher than 142. So that would be on this side. So we're looking to see how much data is to the right side there of that 142. Okay, so what we need to do is we need to get ourselves a z-score for 142. All right, so since we're talking z-scores, I'm going to go back to red here. All right, so to get a z-score, what I do is I take the data value minus the mu, the population mean, subtract and divide by sigma, the standard deviation, the population standard deviation. All right, so my data value is 142. All right, that's the one I'm looking for, a z-score for, minus my mu, my population mean, which is 100, divided by 15, which is my standard deviation there. All right, so now I get a z-score of 42 over 15. All right. Now that's a little less than 3, right? And that should make some sense because it's a little bit on the left of a z-score of 3. All right, so we've got a z-score that's going to be a little less than 3. It's going to be 2 point something. So I know before I even calculate this, my z-score has to be 2 point something. So when I do 42 and I divide by my 15, I get 2.8. Right, so that is my z-score there. So that z-score is 2.8. Okay. So that z-score, 2.8, is what I need to look up on my table, on my z-score table. All right, so let's find 2.8. So I need a z-score of 2.8, right? Or I could think about it this, it's a z-score of 2.80. All right, so the 2.8 is right here. Okay, so I'm going to be looking in this row. Now, because the second digit is a 0, I need to be looking in this column right here. So I need to look in this row here and this column here. So together that puts me right there. Okay, so that says 0.9974. Right? So alright, now remember, anytime you look something up on a z-score, it's always telling you how much is to the left. Alright, so this 0.9974, if I make that a percentage, multiply by 100, I get 99.74% goes to the left. Well, if 99.74 goes to the left, then what I'm going to do is I'm going to take 100% and subtract the left portion of it, and I'm going to get the right portion, which is 0.26% goes to the right. So 0.26%. So about 1/4% of all students at Great Oak are actually considered to be geniuses. 0.26%. All right. So what that means, 1% would mean 1 out of every 100. 0.26% is 1/4 of that. So now it's 1/4 out of every 100, 1/4 of a person, or another way of thinking about that is 1 person out of every 400. So approximately 1 person out of every 400 that you meet, anywhere you go, not just Great Oak, is considered to be a genius level, a true, actual, living, breathing, talking, walking genius. All right. So we know the percentage of people that are geniuses at Great Oak, 0.26%. Okay, but let's go back to the problem. Okay, because if we're talking about geniuses, let's be a genius for a minute and actually read the question. It says, if 3,300 students at Great Oak, notice we haven't used this number yet, so that should be a clue that maybe we're not. I mean, we used the 142, right? But we didn't use this, 3,300. It says, if 3,300 students at Great Oak have their IQs tested, how many of them will be considered to be geniuses? It didn't ask what's the percentage of students that are geniuses. It's how many of them, right? If I asked you, hey, how many cheeseburgers did you order in and out? You wouldn't say, 0.26%. You ordered 0.26% of what's in the store. You would tell me, no, I ordered 3 cheeseburgers, right? Maybe you're really hungry, right? So it's asking how many of them. All right, so what we need to do now is we need to take this 0.26%, which, by the way, 0.26% really means 0.26 out of 100, right? So I need to take that and I need to multiply by how many students are actually at the school. So that's how I get 0.26% of it. I take that 0.26 out of 100 and I multiply by 3,300. Okay, and if I do that, I get 0.26 divided by 100 and then multiply by 3,300. And what I get is 8.58. Right? So since we're talking geniuses again, let's talk for a minute. You can't have 0.58 of a person, right? I can have 8 people, I can have 9 people, but I can't have 8.58 people. So what I would say here is approximately 8 or 9 students. So at Great Oak, approximately 8 or 9 of them would be considered real-life geniuses. So out of those 3,300 people that you've seen walking around Great Oak over your first few years there, about 8 or 9 of them are bona fide geniuses. Okay? Now, I can say that with a very high degree of confidence because normal distribution is a real thing. It's not something that is fake. It's not something that just somebody made up and we pretend it works. Normal distribution works. If you're looking at 3,300 people, that's plenty big enough to be an actual population size, right? That's plenty enough to give you a real, if I just asked 2 people, 3, 4, 5 in a room, maybe that's not enough to really get a good sample. 3,300 is plenty big enough of a sample to make sure that it's normally distributed data, all right? Remember what I said, the more data you collect, the more likely it is to be normally distributed. 3,300 IQ tests is plenty enough to be normally distributed. All right, so this is very, very reliable here. So this is my prediction, 8 or 9 students. Now, if you actually went through it and actually took everybody's IQ at school, it is almost guaranteed that either 8 or 9 students are going to be considered geniuses. Right? You might have a tiny fluctuation, like maybe there was only 7 one year and 10, maybe 10 the next year or something like that. But you should have pretty spot on, pretty predictably 8 or 9 geniuses at the school. So that's kind of cool. There are 8 or 9 geniuses walking amongst us. All right. So now that we've talked about standard deviations and population means mu, and normal distributed data, z-scores, z-tables, all that stuff, let's talk about how this actually relates to the finance section 1.4, right? Probably about time to get around to that. All right, so section 1-4 is about travel expenses. So this is our only real example here of where we're dealing with real travel expenses. Okay, it says the mean hotel hotel rental in New York City is $367 per night, with a standard deviation of $90. Use the empirical rule. Create a distribution of hotel rentals assuming that the data is, this word, normally distributed. I'm going to stop. I'm not even going to read any further because I know the fact that it said normally distributed means I am going to have to draw myself a bell curve. All right, and on that bell curve, I want to go through and I want to label my z-scores. All right, so I know right here at the peak of that bell curve, that's my mu, that's my mean. That z-score is 0 because it's 0 standard deviations away from the mean. It is the mean. All right, my next one, I'm going to have a z-score of +1. The next we'll have a z-score of +2, and the next we'll have a z-score of +3. Okay. Now let's go the other way. Put in a z-score of -1, then a z-score of -2, and then a z-score of -3. Okay, so there are our z-scores. Now, notice I did that without even reading the rest of the problem, and it's because I saw this right here, normally distributed. Anytime I put normally distributed, immediately do what I just did. Draw a, bell curve with the z-scores in there. All right, and then I would suggest putting in the values where they belong. So it does say that the mean hotel rental in New York City is $367 a night. Well, if the mean is 367 a night, let's put that right there. That's the mean. Okay, that's the average. All right, now it has a standard deviation of 90. That means the z-score of -1. If it has a z-score of -1, sorry, a +1 over here. If it has a z-score of +1, it's 1 standard deviation above the mean. So it's 1 standard deviation greater than the mean. Well, the mean is 367, and a standard deviation, so this is our mu, standard deviation is our sigma. Right? So add $90. If I add $90 to this, I get 457. All right, add another $90 to get to a z-score of 2. All right, so add 2 of these. All right, so in other words, add 180. And that's going to get me 547. And then for a z-score of 3, add 3 of these right here, 3 standard deviations, add $270, right? And you're going to get $637. All right. Now let's go through and go the other way. Z-scores of -1 means you're subtracting these standard deviations of 90. All right, so let's subtract 90 here, and that's going to give me, what, 277? All right, then subtract 90 again, that's going to give me 187, subtract 90 again, and that's going to give me 97. Okay. All right, now it says, what percentage of hotel rooms are less than $187? Okay. Well, here's $187 right here, so it's asking, what's the percentage less than that? Okay. Well, 2 ways to do this. You could do this using the empirical rule, or you could do this using a z-table. Okay. So a z-table, you would need to find a z-score of -2.0. So that one here, I would not want to use because this is for positive z-scores. I would want to use one that has, same here, this is positive z-scores. I would want to use one that has negative z-scores. So I would want to maybe use this one. So I'd find -2.0. Looks like right there. 0.0228. Okay. And by the way, I'll go back to that. Notice that 0.0228, it goes to the left. So that means 0.0228. I want to multiply by 100. That would be 2.28%. So 2.28% is to the left. Alright, so when it says what percentage of hotel rooms are less than 187, that's that percentage right there. That is 2.28%. So that's according to our z-score table. Alright, so that's one way to go about doing this. Another way of doing this is, use the empirical rule. Anytime it's asking you about like these kind of values, and those are the ones that are on z-scores of -3, -2, -1, 0, 1, 2, or 3. In other words, it has integer z-scores. You can use the empirical rule. So I'm going to go ahead and do that here. Let's look at the empirical rule on this one. The empirical rule says, the 68, 95, 99.7 rule. But here's what we know. Because this is not just the median, or mean, it's also the median, that 50% is on the right side. Okay? And we know from our percentages that this was roughly, over here, 34%. And we knew that this was about 13.5%. So 50% is to the right of this line. 34% is between here and here. And 13.5% is between here and here. Okay? I could add all those together. I could do the 50% plus the 34% plus the 13.5%. Okay, and when I do that, I get what, 84, 97.5% roughly. So remember, these are kind of approximate numbers. Well, that's how much is to the right. What I wanted was how much to the left. So if 97.5% is to the right, that means the other 2.5 approximately percent must be to the left. Okay, so that's another way of doing the problem. Now notice these do not exactly match. Depending on whether you use a z-table or the empirical rule, they're not always going to exactly match. And because the z-tables give you exact figures, but let's go way back to when I introduced the empirical rule to you. Okay, notice it said approximately 68%, approximately 95%, approximately 99.7%. Okay, so those are approximate numbers, whereas the z-score tables are exact. Okay, so sometimes an estimate is good enough. in which case maybe use the empirical rule. Sometimes you need more of an exact number, in which case the z-table would be a better way to go. Okay. So anyway, a couple ways to figure that first question out. So the first question was, what percentage of hotel rooms are less than $187? Okay, now the other question, the second question, says, if there are a total of 20,000 hotel rooms, how many are less than 187? Now we know the percentage is 2.5%, but I don't want to know the percentage. I want to know the actual number of hotel rooms. So that 2.5% really means 2.5 out of 100. Remember, percent always means out of 100. So that's the percentage. Now I'm going to multiply. Remember, it's percentage of the 20,000 rooms. In math, of means multiply. So 2.5%, that's 2.5% of 100. So 2.5% of means multiply the 20,000 hotel rooms. Okay. Now let's go ahead and do that calculation. So what I have is I have 2.5 divided by 100. And now I'm going to multiply by 20,000. And when I do that, I get 500. Okay. So of the 20,000 hotel rooms in New York City, only about 500 of them are less than $187 a night. New York City is a very expensive place to live, very expensive place to visit, right? There aren't very many hotel rooms less than $187 a night. And those are your examples. That is what you need to know about normal distribution, the empirical rule, which is the 68, 95, 99.7 rule. What you need to know about finding z-scores, but you also need to know about what to do with the z-score. So when you find a z-score, the whole reason of getting a z-score is so that you can look it up in a z-score table and find the percentages. And please, please, please remember, when you use a z-score table, it's always giving you these percentages are what's to the left of that z-score, what's less than the z-score. And when you need numbers to the right, think, hey, if 90% is the left, then 10% must be to the right, right? If 75% is to the left, then 25% must be to the right, right? And that, I believe, is it for section 1-4.